Okay, hey everybody. Thanks for coming. I should take my badge off. My name is Max Ogden, and I want to talk about a thing that JavaScript isn't as good as other languages at yet, but I think totally could be if we can create kind of a community awareness and momentum towards it. And that thing is science! Exclamation point. I also have some cats sprinkled in this presentation. And I took all the cat photos, so I don't need to CC license anybody but myself. So I work on a project called DAT, and it's a grant-funded open source project. And what we do is we try to take the cool stuff that happens in open source and computers, and then get scientists to use them. Because the nature of most scientists is, in the way they get funded and supported in their work, is that they get rewarded for publishing papers in journals, but those journals don't give them incentives to write good code. So we get paid by companies and different places to write really good code, and we never have to write academic papers about it. And on the other side, it's kind of the opposite. So I think there's a really interesting overlap potentially in the middle, where we could try to get more of the things that we learn about code and how to make computers do awesome things for us. And we built an ecosystem like NPM where we can have hundreds of thousands of packages being published freely, and that kind of open ecosystem stuff really needs to affect science more directly. But the problem is a lot of scientists aren't using JavaScript today because they're kind of stuck in the what I call pre-V8 era of thinking about JavaScript, aka when JavaScript used to be slow and awkward, and now at least it's fast and awkward. So at least we have that going for us. But I think it can be a lot better. So I don't necessarily want this talk to be about like standards bodies and everything. Unfortunately, a lot of it kind of comes down to, at the end of the day, how do we get JavaScript to be better? We have to find our local representatives. It's kind of like vote. It's like voting. It's like you have to meet. If you find a cause you really want to support, you have to email your representative, email your senator. And I think we should be maybe not emailing. Maybe TC39 would get mad at me if I told you to all email them right now. But find ways to find our representatives. TC39 is like our democracy. We need to get them to care about this stuff because we're underrepresented in terms of asking for things that scientists want that could make science better so that scientists could just use the web. One of the big issues with science today is reproducibility. And that basically means, how do I get your code to run on my computer? Which we've basically solved in software engineering. We have things like Travis CI, which proves even before you start wasting your time if somebody's code is going to run on your computer. But there's nothing like Travis CI for science. There's nothing like even test suites for a lot of scientific code that's published, if the code or the data ever actually does get published. So, I mean, the web is the perfect reproducibility mechanism because you go to a URL, and if you want the newest version, you hit refresh, and you have it. You don't have to download a specific version of a C compiler, and you don't have to be on a certain Linux kernel version. So the only problem is we're kind of missing some primitives that they need to do their actual work. So I started a group recently. This is like the first public announcement of it. It's called Code for Science. And it's not even a thing, it's just a GitHub org. It's not an actual organization in the real world, really. It's basically an open discussion forum and a Gitter chat room. And it started by me and then a friend of mine, Jeremy Freeman. And Jeremy's in this really cool place called Genelia Research Lab, and it's part of the Howard Hughes Medical Institute. And I think it's one of the coolest ways of funding open source projects that I've seen almost ever. Basically, Genelia says, hey, if you're a lab leader, we'll give you 4 years, we'll give you a bunch of money, you can do whatever you want, you can spend your money on whatever it is, as long as it's the pursuit of understanding the human brain, if it's underneath that umbrella. So the way that Jeremy spends the budget from his lab is they try to understand the information that comes out of the microscopes and all the imaging things that people are looking at people's brains and different organisms' brains, and they aren't able to use things like Spark for distributed computation. They're not able to share their code freely on the internet, so they built some stuff around a thing called IPython notebooks, which is really cool, to make them runnable with Docker containers so you can deploy them easily and be able to one-click share your code or have a link from your GitHub repo that runs the actual code somewhere. So they're kind of trying to take distributed system stuff and make it accessible to people doing brain research. And I just think that's a really cool way to fund open source, and I'm really interested in getting the different people trying to work on open source projects, but maybe their organization isn't a full-time organization writing open source code. Most aren't. But if we can kind of pool all these different interests together, then we can do some really cool community projects. So the Code for Science, basically the goal is just get the coders, get the scientists together, get them talking about what the frustrations are on either side, and see how we can kind of share at a high level, especially across communities. Like I think JavaScript could learn a lot from this thing called the PyData stack, which is a bunch of really awesome tools in Python for doing scientific computing and numeric computing. And it's just everything in the PyData stack is basically missing in JavaScript. Up until very recently, there's been some really awesome work on it. But you know, we should be trying to learn from other communities and see how we can make JavaScript compete on this front. Because JavaScript's pretty good at web apps, pretty good at web servers, pretty good at networking. We kind of fall down when it comes to things like numeric computing. So you can check out Code for Science on GitHub. It's GitHub/Code4Science. And there's a couple repos already, actually. Basically, I've been inviting all of the cool scientist people that I've met and a bunch of interesting coders as well. And so they've created some different repositories just to act as discussion forums using GitHub issues. And there's one on distributing computing. There's one on data packaging, so like data formats to share on the web and otherwise. There's things on doing data pipelines. There's well, just a general community one. So if you don't even know, if something's very unclear and you're like, hey, I'm a newbie to this, I don't understand what these concepts, open a community issue and just be like, this information is missing, I'm a newbie. That's actually really valuable feedback. But then the one I want to talk about today is called WebData. And WebData is, I've broken it down into these discussion points. So actually, this is my next slide. I used cat emoji 2 for my bullet points. So this is my summary after years of working on this stuff of what's missing in the web. So I would say that JavaScript does most of these, well, specifically the browser JavaScript does most of these really poorly. Node does some of them well. And so I think there's a lot that even browser JavaScript can steal from Node, and there's especially a lot more that all of JavaScript can steal from other places. So I'll just go through these. The first one, precision arithmetic. It's really funny when you go to talk to people that work at like JPL, and they're like, oh yeah, so about those 32-bit numbers in JavaScript, we do like rocket trajectories, and we have to land things on Mars in like 7 years from now. And that extra floating point precision can really come in handy sometimes, and being able to do fast, real-time computation on, like high precision multiplication of numbers is really important. There's some libraries. For instance, there's one called bn.js that exists to implement a big num, which is basically things larger than a 32-bit integer and doing different arithmetic operations on them. You can write things like this, but when it comes down to it, when you actually have two numbers and you want to multiply them, you have to do it all using hacks in JavaScript math, and it can be slow. So there is actually, for all of these, I basically went to TC39's stuff, and I found if there was a proposal. I actually did find a proposal that Brendan Ike has edited recently, maybe because I've been starting to like link to it and stuff. And there is actually a proposal that's been presented to TC39 about adding some really cool stuff to JavaScript's math keyword, or global, to allow you to do 64-bit operations on numbers. And this would basically just make these big num libraries a lot faster. And so this actually seems like a really low-hanging fruit. And then I looked at it further, and I found out that it was actually never added to TC39's proposals. So I sent a pull request recently, and I added it, and they even said, oh, how did we forget to add 64-bit integers? Basically, no one cares about 64-bit integers in the community, I found out, enough to even remember to put it on the thing that they talked about. But more importantly, not to like crap on them, because when you look at the TC39 proposals list, there's like 50 things, and each one of those is its own huge argument, basically. About getting stuff into JavaScript and whatnot. So I can't blame them. I think that the standards body actually, given the number of JavaScript developers in the world, the amount of people who actually influence what gets into the language is really, 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 really small. And so one issue is that there isn't actively what they call a champion on this proposal, which means that there's basically nobody working on it. So if anybody here knows somebody that's really passionate about high precision numeric computing and the web, link them to the Code for Science web data repo, tell them to get involved in this issue, and we can figure out how to get them to help TC39 prioritize this. Or if you have feelings about this, you should just leave a comment. So I think that this one, specifically 64-bit ints, is actually really representative because it's not that controversial. It doesn't break backwards compatibility. It's not even that hard to implement. It's basically just saying JavaScript can't access these things that CPUs can do. We want to add new things to the math library so that they can do this stuff faster. I don't really see a downside. I'm not really in the standards body though, so I could be overlooking something. I'm not an expert on these things, but I figure if we can do this, this would be a really awesome win. But I want to go on to other things because I have about 10 minutes left. So this is actually the biggest issue with a lot of stuff, is a term I borrowed from my friend Mykola Lysenko, who writes a lot of awesome Node modules. And he summarized the problem with most JavaScript stuff as memory bandwidth. So it's, if you compare, say you want to have a bunch of numbers, put them into an array in memory so you can do some sort of computation on them, the amount of overhead in terms of just memory, like if you look at the actual raw memory table, the amount of overhead you get with JavaScript is a lot higher than in C. And that's because you have things like objects that you have to wrap around the actual raw data because everything in JavaScript is an object. And so when you create an object, that takes up memory. When you access something, you actually have to look up the object pointer in memory, which points to another actual address. So everything gets slowed down because there's all this indirect access and pointer dereferencing happening at the low level. There is a proposal, this thing called typed objects. And the quick summary of these things, I might be butchering this, is there's a thing in C called structs. And they let you lay out memory in kind of custom ways really efficiently. And typed objects are basically the closest thing we can get to struct-like efficient memory packing in JavaScript. And then there's another proposal called value types, which is basically a way to extend JavaScript's built-in types, which are things like number, object, string. And you can actually have new types that basically what that means is the JavaScript compilers will be able to optimize the every time you access data in a value type, and typed objects and value types are kind of this coupled proposal. And if you create a custom type, you don't have to always go through JavaScript objects to get to it, which means you can reduce the amount of bandwidth needed, or the amount of memory needed to represent the object in memory, and also the memory bandwidth, which is how slow it is to actually get to the data you're looking for because you don't have to always go through object. The sad thing about this proposal is it was actually active. It was actually on TC39's official proposals. They have a stage 0 proposal and this is stage 1 proposals. Stage 0 means it's an idea. Stage 1 is like somebody's championing it and it's actually been presented. This was actually like stage 2 or something, but the issue with it is for 2 years it hasn't been worked on. And when I opened an issue and I was like, hey, I noticed that this was 2 years old, there isn't really a new link, they were like, oh yeah, we've been meaning to remove that because it's been inactive. And I went, are you serious? Like, this is such a cool, this would add the ability to do so many cool things in JavaScript. For instance, highly dimensional array operations, so like things like n-dimensional array, which is really important for matrix, or like 3D data, doing volume operations, doing like fast Fourier transform, a lot of really cool stuff that people do in SciPy. It's just slower because you have to use JavaScript objects on top of typed arrays. If they could do it in a lower level way, it'd be really cool, but this proposal hasn't had any steam lately. So for at least a year and a half, around a year and a half, 2 years, the previous champions have basically fallen off the face of the earth from what I can see, and there isn't a new champion. So again, we have another really cool proposal. This one's a little bit less of a low-hanging fruit because it's adding, kind of something fundamental to JavaScript's built-in types. But when it was presented to TC39, I think it went over well. So this is another thing that I think that we're kind of, it'd be cool if we could give some attention to and tell TC39, hey, we really want this stuff in JavaScript as well. And you could read about my summary here, and I'll go on to the next one though for time. So this one is even wider of a scope. I actually had a lot of fun writing all of this because it was fun to research all the active proposals. But basically parallel data processing, and it boils down to there's two types of parallelism. There's doing data parallelism, which is things like actually one of the brightest lights of this research that I did, there's a proposal called SIMD, S-I-M-D. That's an optimization CPUs can do, where you can do operations on multiple pieces of data at once in the CPU, so you can get like 2x, 4x improvement and do a lot of really efficient caching. So there is actually a SIMD proposal that's like fairly late stage in TC39. It looks like it's going to get in. And so that's really cool. What I've been trying to figure out is like, why did SIMD succeed and typed objects and 64-bit integers haven't succeeded? But it's also really hard to find information about this stuff. So concurrency and parallelism, data parallelism is things like SIMD, where you have one CPU process or one CPU that's editing a bunch of data at the same time. That's kind of like a CPU optimization. There's also task parallelism, which is things like threads. Famously, JavaScript is single-threaded and Node is single-threaded, even though there's things like web workers and Node V8 worker threads under the hood. But how cool would it be if we had, well, this might be an overstatement. How cool would it be if we had access to low-level parallelism and concurrency primitives in JavaScript, just for, in case we need it, because what people always say is, oh yeah, I was using JavaScript and then I had to like do some quote-unquote number crunching, so then I went to something where I could, utilize all of my CPUs. So there are actually a bunch of proposals you can read about here, and there's some interesting ones, like for instance, there's a technique of writing lock-free algorithms. So this is not using mutexes, but it's basically using this thing that CPUs can do called atomics, which is, you can read about. I'm not going to try to explain here. But basically, there's a bunch of really interesting proposals, and again, these are all really early stage. So this stuff would really help people doing really performant computing in JavaScript, because it would let them crunch numbers faster. I think I forgot to mention on one of the other ones also, there's like limits on how big a JavaScript array can be, which means I work with a bioinformatics person who studies DNA, and they have a machine that has 512 gigs of RAM, because DNA is big, and they need to be able to put it in memory so they can basically sort it a bunch of different ways. So that's a lot of RAM. That's more RAM than I think my last laptop had hard drive. And in JavaScript, you can only create 32-bit number long arrays. So they have to drop down into lower level languages to utilize those kind of computers. So this is one thing that Node does really well, file and network I/O. So Node does it really, really well. I think Node basically showed that JavaScript can do file and network I/O really well, but the browser hasn't really caught up yet. And you could read about these proposals in the browser. I've basically summarized years of working with I/O in both browsers and Node, and kind of said what the goods and bads are. And what I think is really cool about this thread specifically is that the first comment was from the person who works on Google Chrome on IndexedDB. I don't even know how they found this thread, because I only shared it with a couple people. But they were basically saying like, hey, we're working on this on Chrome. So we're already getting the attention of some of the browser people. So that's really cool. So hopefully we can get, my dream is if I can get scientists and like Chrome and Firefox people to talk to each other directly, and get the standards bodies in there too. And a bunch of, web people being like, we would want this too for this use case. There's a lot of like analytics stuff that is involved in this. There's a thing called IndexedDB in browsers specifically, which is like the only way to write data into a browser. The first thing you ever do in data science is like read a large file and then do something with it, and then maybe write the file out to disk. But that workflow is actually almost impossible using browsers directly. You have to do things like write the file into a database and then save that into a file later, and it's really slow. So there's a really simple thing that we could do in browsers, which is allow browsers to stream data to users' files after they've given permission, obviously. But there's a lot of really simple things that browsers could do to match Node's streaming performance. So if you're a Node person and you're ever talking to browser people, show them how streams work. Show them how easy it is to do FS, use FS to pipe things to and from things. Like do a file copy by piping an FS read stream to an FS write stream. Those concepts are kind of foreign to a lot of, even the people that work on browser standards. They're not thinking of the browser in terms of networked I/O, but I think there's a lot of stuff that we can steal from Node to make that better. There's a thing called WebAssembly, which could also affect a lot of this stuff, because it basically means you could run a compiled, basically intermediately compiled like binary, almost like a C native add-on in the browser. And so if you can write all your code in this VM and not even use JavaScript, then it's kind of the same as writing a Node native add-on. But that kind of raises some questions too. It looks like WebAssembly, it's not part of TC39, it's kind of a broader thing, but it does have some pretty good momentum. And there's some good discussion going on in here as well. And there's doing computation on the GPU, which I'm not an expert on, so I'm not even going to try to explain, but basically using your graphics card to do math from the browser, which is useful in certain situations. And the last thing is n-dimensional arrays, which I already kind of mentioned. The cool thing is you can almost implement these in JavaScript today pretty efficiently. They're not quite as efficient as being able to do it in C because of memory bandwidth stuff, but you should definitely check this out if you want to see. There's some people really trying to make this work today on the web, and I think this can really inform what comes later. So I also tried to do an introduction you could read in the README. Again, I'm about out of time, so please check this out. And especially if you're the right person, if you know somebody that's the right person that would really want to help summarize what we need, improve this stuff, and then we can take this to standards bodies and be like, hey, we want this in browsers. Definitely get involved. Yeah, that's the WebData repo. It's Code for Science on GitHub/WebData. We also have a Gitter chat room you can just hang out in, and basically there's a bunch of scientists in there now talking about random stuff. It's really fun. I learn a lot every day. And thank you for coming.